If you take a complex polar graph, like a multi-petal rose curve, and unwrap it, you're left with a simple, repeating two-dimensional line. Every polar graph you will encounter is exactly this, a standard Cartesian wave that has been wrapped around a central point. To draw these by hand, we use the 5 key points method, sine and cosine waves. We will draw our standard wave on a Cartesian XY grid and then map it onto the polar grid. By mastering this translation, you remove the need to memorize dozens of specific polar formulas. The graphing process becomes a direct geometric mapping of your wave. We'll apply this method to the equation r equals -2 cosine theta plus 4. Look at the plus 4 at the end. That is our vertical shift. The vertical shift tells us the exact center of our standard wave. So our midline sits precisely at 4. Next, we look at the amplitude. The coefficient of 2 determines how far the wave stretches above and below that midline of 4. To find the ceiling, the highest point of the wave, we add the amplitude to the midline. 4 plus 2 equals 6. For the floor, or the minimum value, we subtract the amplitude from the midline. 4 minus 2 is 2. We have defined our vertical bounds, 2, 4, and 6. This cages the mathematical behavior of our wave before we plot a single coordinate. Now we establish the horizontal layout by determining how much distance on the x-axis the wave needs to complete one full cycle. The period formula is 2 pi divided by b. With an implicit 1 next to theta in our equation, the period remains 2 pi. To find the precise distance between key points, calculate the interval by dividing the period by 4. 2 pi divided by 4 simplifies to pi over 2. We mark our x-axis at 0, pi over 2, pi, 3 pi over 2, and 2 pi. By intersecting these horizontal intervals with our vertical bounds, we lock in a grid. The path of the wave is now entirely predictable. At this stage, errors usually happen deciding exactly where on the y-axis the first point belongs. Sine waves start at the midline. Cosine waves start at their maximum amplitude. Our target equation has a -2 for its amplitude. Because it is negative, the starting point inverts. Instead of starting at the ceiling, this cosine wave begins at the floor. Let's look at this Cartesian graph to plot our 5 points. We start at the floor coordinate of 0, 2. At our next interval, pi over 2, we hit the midline at 4. At pi, we reach the ceiling of 6. At 3 pi over 2, we return to the midline at 4. And at 2 pi, we finish where we started, at the floor of 2. Connecting these 5 dots gives us an inverted cosine wave. This standard 2D wave contains all the geometric data we need. We are ready to translate it into a polar shape. To translate from Cartesian to polar, the x-axis values become the polar angle, theta. The y-axis values become the radius, r. Point 1 starts at 0 on the x-axis and 2 on the y-axis. On the polar grid, we go to the 0 radian angle and place a dot at a radius of 2. Our second Cartesian point is pi over 2, 4. We move up to the 90-degree angle on the polar grid and push out to a radius of 4. Our third point is the wave's peak at pi, 6. On the polar grid, we rotate to the 180-degree angle and plot our point at the maximum radius of 6. For our descent, the point at 3 pi over 2, 4 maps to the bottom axis at radius 4. Finally, our point at 2 pi, 2 brings us exactly back to where we started on the right side. Looking closely at this polar graph, we draw a continuous loop connecting these coordinates in order. This forms a dimpled oval shape known as a limacon. The rise and fall of the wave translates precisely into how far the polar curve expands or contracts toward the center point. Here is the complete side-by-side translation. The 2D geometry maps directly into the 360-degree polar space. The accuracy relies on calculating the ceiling, midline, floor, and interval. Consider what happens structurally if your floor calculation results in a number below 0. Let's graph the equation r equals 4 cosine theta minus 2. The vertical shift pulls the floor to -6. This graph shows what happens. When the Cartesian wave dips below 0, the line passes straight through the origin point and draws on the opposite side of the grid, creating an inner loop. The 5-point rules are absolute. By setting up the Cartesian grid and translating it point by point, you can accurately map any polar equation without guessing.